So mid-sentence here. So inscribed circumscribed. The circle, I guess I could type, I just realized, is inscribed in, come on, fit it, in the triangle. I'm not going to write this on the next one. That means the triangle circumscribes, there's that pen, circumscribes the circle. And again, I'm not writing this on the next one. I may say it. There's the pen again. Literally like 40 to 50 times in a lesson. Write. And I got to keep rewriting the letter for the pen to actually work. Love it. Circumscribes the circle. Okay, so that's not what I was talking about before I started the video about a theorem you'd have to literally write down. And if this happens, then that happens. Here's the actual theorem. Actually, when you look at this picture, you have something else going on from yesterday. What would we call those two segments when they hit the circle once and only once? It starts with a T. 3, 2, 1, go. Tangent. Those are tangent lines coming, or segments, because it does, I'm stopping it at the point of tangency. Those are tangent lines coming from the same point. And then the theorem that C.M.E. Samuels would have to write is, if two tangent lines are hitting a circle coming from the same point, then those two tangent lines would have to be equal in length. I'm just going to mark it. We're not going to write that down formally. If two tangent lines are coming from the same point hitting a circle, then those two tangent lines are congruent to each other. If two tangent lines are coming from the same point, then those two tangent lines are congruent to each other. Kind of feel bad. You did do proofs last year, right? Were any of them 10-steppers, honestly? No. They're getting, they get pretty big. And actually I had Brianna Samuel. She had it as a sophomore, and those were just, I actually don't like teaching geometry of all the math classes. I don't like that logic. It is logic, though. It is good brain stuff, but blah, 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 blah. So there's an added theorem, and I'm going to throw a few more at you today, and just, hopefully common sense will make you know that for the questions when I look at the worksheet. All right, not writing it, but this triangle is inscribed in the circle. The circle circumscribes the triangle. Just one more thing, though. What are three angles in a triangle? What are three angles in a triangle? 1, 2, 3, go. What do they have to become? I'm sorry. 180. Sorry, bad question. But then also remember that these three angles are actually inscribed. So they actually are half of the arc that they cut. And a full circle is 360. Half of 360 is 180. So there's a reaffirmation of that. Probably one more thing I should do over here. Try to draw a circle and then draw a quadrilateral, which we do have. And I'm not going to make it special, like make it look like it's a square or anything like that. But what you should know about a quadrilateral is the sum of the angles is actually 360. And a little different this year. You don't care what I did last year. Last year was a transition year with our new books and fresh, and plus COVID the year before. We did some other subjects that we didn't do this year. Well, now this year we're going to add quadrilaterals and polygons, which are 5, 6, 7, 8-sided figures and beyond. We're really going to hit that even further. But for right now, we might have a quadrilateral in there. One more time, though, this is weird, but it's because they share, like these four arcs get shared between these inscribed angles. So, for instance, this angle right here cuts this arc, right? And it's going to be half of that arc. But then when you look at this angle, which I don't think this is going to work out too well, try to stay on the outside. When I look at this angle, it cuts that arc and that arc. So you can see right away this arc's being used twice to get these angle measures. All right, what's 2 times 180? What's 2 times 180? 360. Because those arcs get used twice every time, like to find those inscribed angles. That's how you get a sum of 360 from this kind of idea. And actually, what I did there right there is how you'd find those angle measures in a quadrilateral that is inscribed in a circle. Easy for me to say. All right, easy for you to say. It's a great song from the Foo Fighters. Anyway, anyone know the Foo Fighters? Be amazing. Did you know that song that I was talking about? Not yet, not yet. One of these days. Anyway, I can't think of the name of the song real quick. I'm losing my mind right there. Okay, so I'm going to give you some measures. Like, say we say this whole thing is like 10. I don't know. I can't think of questions where just making up numbers. Then let's say this one over here is 3, and let's say this one over here is 7. Okay, and that might be all that she gets. I kind of call this a walk around question then. All right. And the marks weren't there. So you have to know, okay, tangents coming from the same point are equal to each other. Well, that's a coincidence. I didn't mean for that to happen. So if this is 3 and the whole thing is 10, then this is 7. I didn't mean for that to happen. They don't look like they're equal, but you got to trust the numbers, not the way this looks, kind of thing. Maybe they do look equal anyway. All right, and if that's 7, then that's 7. All right, that's because these two are equal. It has nothing to do with these over here. That was the accident I just kind of created. So what's the perimeter of that triangle? Now you could do that. You could add all those sides together. So knowing a common or a tangent line coming from the same point, tangent lines, they're equal when you have this inscribed circle. That's what kind of happens with that one. And when we go to the worksheet, we'll see that we have quite a few of those. Okay, forgot that I didn't give you a printout because we're actually almost done. It's really not going to be a long day. Okay, now remember, this is, we had the same drawing yesterday, but I talked about the angle measures, all right? I talked about the angle measures as half of the sum of the two arcs that they cut. But now we're going to talk about side lengths. What is the relationship with chords? I'm going to write this one in 2 ways. It is a proportionality, and we can't kind of treat this like our proportions that we had in a previous chapter. As a matter of fact, look at your worksheet. Look at page 4. Page 4 is like a nice thing to look at, the very back of the thing. That's a complete and total 100% review. When I did this at Lewis, page 4, the 4th page. Keep going. There you go. All right, 4th page. Those are those similarity statements, right? Those proportionality kind of questions. And actually, you have a proportion in this one, but I'm never going to write this first one again. But it is, as you would expect, AE over DE. You know, you stay on the left side, and this over this equals this over this, top over bottom, or else you'll screw this up. You did top over bottom on the first one, top over bottom on the second one. But when you cross multiply, then AE ends up getting multiplied by its other part of its segment. Oops, sorry. AE, that was my mistake, not the pen that I've been complaining about all year long. That equals this part of the segment times itself, the other part, I mean. All right, when you cross multiply. And that's how I'm always going to write this. ED times EB. I ran over a line. Second time I did that. Yeehaw. Oh, no. Grabbed too much of that letter. Oh, tragedy. Fumble. Okay. Right. So just something to know about that. So that's what I do because of the next ones. And then notice in my notes, I sectioned this off just like I did yesterday, except I think I had this up here and then the other ones below. And then remember, for this one, it was the sum of the angles, half equals, or sum of the arcs, half of that equals the angle measure. And then this one was subtraction. So all three of these drawings had something different. Sorry, I'm going to do my secant first. All right, but in this section, 1, 2, 3 parts of this section, this is the statement I want you to have memorized. Outside, pen, times whole equals outside times whole. And I could set up a proportionality statement that goes along with this. So I'm just going to stick with this trick, this thing that you're just going to have to memorize for this. Oh, and by the way, I'm going to highlight these for you highlighters out there. Outside times whole equals outside times whole. You feel free to do that as well as you mark this and you mark the drawings. The first one I'm going to do is the secant. So now remember, we're not talking about the angles. We're not talking about relationships with these sides. So, and it is a proportionality is what's coming out of this. It could be the same thing. This over this equals whole over whole, and then we could cross multiply. But ultimately what ends up happening is this. Outside, which is AB, times whole, which is, this is how you want to write that so you're not overdoing or overwriting your other highlight, which is AC. And that equals outside AD times whole, which is AE. Right? And then that's it. You got numbers. One of them will be a variable probably, and you play the little game of algebra solving. All right? Really a true story. So then it gets, that's why I wanted to start with this one, because this one is easy and it makes sense. And, you can see an outside part and a whole part. But then now it gets a little bit weirder because that tangent line or segment up at the top, all of it is outside. So how am I going to cover this? Take a deep breath. Go ahead and draw your tangent secant. And take the secant, which now, okay, fine, I get that. That's the outside, AC, times the whole, which is segment AD. That's easy. Got it. No big deal. Well, how do I handle this tangent line? Do the same thing. All of it is outside, so color it as outside, equals AB, and then all of it is outside, and that is the whole segment. So what you end up having is AB outside times AB again, which is AB squared. All right? So I can rewrite that as AC. You don't have to. You could just keep it as outside times whole equals outside times whole and leave it as AB times AB. Whatever AB is squared is what ends up happening there. The last one we've already covered. All right? Didn't we just cover and talk about when I have common, I shouldn't say the word common because that's coming up later, two tangent lines coming from the same points, those two tangent lines must be equal to each other. But if you really wanted to play outside times whole, I just hate when my pen doesn't react. So much wasted time and added stress with this stupid computer. Do you hear me, YouTube? You could do outside times whole equals outside times whole, which is AB times AB equals AC times AC. And then when you square root both sides, you just get AB. There you go, pen. Thank you. Equals AC. And that's really what you just should do on that. So I guess outside times whole equals outside times whole would still work for you. All right. Not really a big deal. Got some stupid little Mickey Mouse questions next in order to kind of exercise the idea. Okay, 685X. All right, kept it simple today. I know on our final review sheets, we got some, that's when we start getting some algebra going on, some factoring, foiling, all this other stuff. Well, let's talk about this one first. outside, which is 6. Pen times whole. Now, what is that? Is that 6 times 8 or 6 plus 8? 3, 2, 1, go. Plus. Okay, it's not 6 times 8, it's 6 plus 8. That is the, how long that segment is. 3 times, right, that equal sign. Equals 5 times, the reason I went over that last one is, what is this? I will get a very, very high amount of people, not 50%, but a high amount of people that will call that 5x. It's not 5 times x, that is 5 plus x. Rough. That was me, even though 5 plus x. Oh my gosh, oh my gosh, oh my gosh, pen. All right, so anyway, making sure you know that that's a sum. So I guess that's the only reason I'm kind of covering that. 60 plus 24 is 84. That's how you mental math that one out. Okay, little distribution. Just imagine, though, if this was x, then you'd have x times x plus 5 if I switched them. Then you'd have x squared, and then you'd have to solve by factoring. Or the anyone? Quadratic formula, the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Nobody? To b and a nothing? You want to sing that? Okay, and then 59/5, just leave it. And then the next one, these are chord. I just think it's more direct to say 9 times 20. Take those two parts. There's a times missing from the pen. Equals, I don't care, x times 8 or 8x. And then solve. That's 180. Pen again. Divide by 8. I think 4 goes into 180 45 times. And I don't know why I wrote a 49. That was not the pen. That was a bzz. There's the pen. No, thank you, pen. There's the pen again. There's a brain mishap there. Okay, and then a couple more things to bother you with, and then I'm going to go to the worksheet and make some notes of stuff that you should know, not that you should know now, that I need to kind of express to you. Okay, here's actually a written in theorem form. Okay, so if L is tangent to circle C at point A, then L is perpendicular to CA. Really what it should say is, if a radius hits a tangent line at a point of tangency, then they are perpendicular to each other. That's where proofs get real annoying. You'd have to state that, then you'd have to state that that angle is 90 degrees by definition of perpendicular, and that's where it just gets the logic is annoying and a little overdone. I think. I'm just not a big algebra or geometry person. At least proofs. I do like geometry figures, just not proofs. I'm with you on that one. All right. Had to work with Sammy this year in some proofs, and it really depends on the teacher. He can be a real stickler on stuff if you don't have every little thing logically denoted. And then real quick on this one, you got to trust the drawing. It looks a little bit off. Seems like, no, I think I got this drawing from someone else. I don't think I drew this one. All right, but those are points of tangency. So actually what you have here, how do you get x? You actually have a quadrilateral. And actually this, does anyone know what this quadrilateral is called? Sometimes you fly this outside. 3, 2, 1, go. It is a kite. Because actually these two have to be equal because they're radii. And these two have to be equal because they're two tangent lines coming from the same point. That is the attributes of a kite. That's going to be in our quadrilateral section. Okay, so those are 90 and 90 because of what I just stated before. And then since it is a quadrilateral, all 3 angle measures equal 360. Sorry, all 4 angle measures. So this is how you'd find, and you can just go ahead and type this and get your own answer. 180, I guess that leaves 30, I think, right? Leaves 30 degrees. Pretty simple. All right, let's snap to the worksheet real quick, and then I'm going to leave what I had with the others that I wrote down. Some stuff here. Okay, so go to page 1. Well, that's what this is all about right here. All right, number 2 is almost exactly like the one I just did, except 130 instead of 150. And then right here, that's a point of tangency right there with the radius hitting it. So what's that angle measure? 3, 2, 1, go. 90. You have a right triangle, which then leads to this. Okay, I added this because to help you, so you don't. I should have let you struggle and try to figure it out. But how come I know this one's 9? Because it's a what for the circle? A what? 3, 2, 1, go. No, it's a radius, and all radii are congruent. So if that one's 9, that has to be 9. No, AC is not 9x. What is it actually? 3, 2, 1, go. 9 plus x. Shouldn't have done this for number 4, but I'll go ahead and show you. All right, and then I'm just going to have you write this down, and I'm not even going to look at this algebra like we're going to have a question about this. We used to have questions about finding that common external tangent line. What is x? Sometimes it's either find x or find the common external tangent line there. So I may have done a little mistake last hour, but it's okay. I'm going to erase this. But I just want you to know these terms. And the term is common external tangent because it's on the out. Of course, it has to be on the outside of the circles, but it's not in between them. This is called a common internal tangent because it's in between those two circles. Then I just left it at that. We're going to shorten this up here as far as the things you need to know. Okay, so just define those. What is the name of ZY in each drawing? That's what they're called. They do have attributes, and there's a way that you could solve for X. Actually, not too bad. All right, and then moving along here, these are pretty simple. I just asked for, and look at it where I put polygon, change that to polygon. It's the first time I noticed that. I never noticed I had a little typo in there. I already showed you how to do this. This is the classic walk-around question. Knowing that these segments are equal to each other. Very simple. So walk around on that one. Cross this number 13 off. Destroy it. Here's another theorem I should actually define, but hopefully this could be common sense. When you have a chord, let's call this like a radius if we kept going through this. If a radius is perpendicular to a chord, then it bisects that chord. That should actually be something we would write down as a theorem. But go ahead and mark that real quick. When this is a right angle here, then this bisects this chord. It has to happen in a circle. Okay, and then that was really what dictates number 15 as well. So you're going to find this, but then to find x, you just double it because those are equal there. So again, because of that right angle being there. And then one more thing. Here's a theorem we'd have to literally write. When chords are equidistant from the center of a circle, then those two chords are equal to each other. So what does x equal, everybody? 3, 2, 1, go. 3. Pick 3. All right, and then same old. You should be able to figure out those. I love this. Put a star by 18. Love it. Next, I gotta find questions that do more with factoring and foiling, and more with trigonometry. All right, because it could be trig that we could use on this. But one thing to know. This is called drawing an auxiliary line. This is not in there, but you make it happen. So draw it right now. So draw it. Again, what I just told you is when you draw perpendicular, it bisects that chord, but it also bisects this arc. So what are these two angle measures in here? What are both of these? 60. I wonder if that's a special triangle. So yeah, you should be able to figure that one out. That one's pretty easy. All right, and then these are from yesterday. I think I have a quadrilateral. Don't look at that. I don't want you to. But that's what you got to do on that. There's some stuff going on. Wait till you see what I got Monday. This is awesome. Monday's going to be fun. You should be able to do that one. Fill in some parts there. Should be able to do that. Then there's the quadrilateral stuck inscribed in a circle. So I picked an angle. I picked angle A. By the way, what's the full arc? What does it all add up to become? So you should be able to find that pretty easily. And then looking at angle A hits this arc. Oh, so it should be half of that. All right, and then that's how you end up getting it. But why do you end up getting 360 in this? 60 is going to be bisected numerous times. Like angle B bisects that 60 and 100. So, each arc gets bisected twice by one of the angle measures. So they're double counted. Yesterday. A little bit of yesterday and today. Just to look at this one real quick, to conceptualize real quick. By the way, a full circle is how many degrees? 321, 360. And then angle Y is a tangent angle. It is half of big arc minus small arc. And then that's how you end up getting that. Okay, so you got to be able to see that within the picture and use your eyes correctly. This is an inscribed angle. So what is that arc that it cuts? This is an inscribed angle. So what is that arc that it cuts? So now you should be able to find X. All right, and then this is we were talking about you, Caleb.
Oh, really?
When you miss class, where do you look? Uh-oh.
Attendance office?
Oh, my goodness.
I don't.
When you miss my class, where do you look?
Oh, no, yeah, now I know.
Now you know it. It's almost April. Okay. All right. Goodbye, everybody.